Let's solve Unit 10 Artificial Intelligence questions. Arrange the following examples of artificial intelligence in the order of increasing complexity. Let's first see the options. Spam email detection using rule-based systems. Rule-based system in the sense there will be certain rules like if and then conditions. So this will be in the format of if, then, action, or there will be an else action. The next example is handwritten digit recognition using shallow neural networks. If you take neural networks, there are two kinds. One will be shallow networks. What is shallow networks? You will not have so many layers in between, the input layer and the output layer. If you take deep neural networks, there will be lots of hidden layers in between input layer and output layer. So this will be less complex than deep neural networks. Next example, image classification using convolutional neural networks. If you would have watched the deep learning series that is in my channel, there is a playlist. If you want, you can have a look at it. There I would have explained an example of convolutional neural networks. If you go to that example, you will find lots of calculations in between the input layer and the output layer. So this is quite complex compared to the shallow neural networks. This is actually a deep neural network algorithm. So between B and C, we can say B has less complexity than C. Then the fourth example, autonomous driving using reinforcement learning algorithms. In machine learning, we have three types. First one is supervised learning. The next one is unsupervised learning. And the final one is reinforcement learning. Whether deep neural networks are complex or reinforcement learning is complex. Deep learning is learning from a training set. Once the neural network learns from the training data, it will apply that learning to a new data set. This is the concept of deep learning. In reinforcement learning, it will learn by adjusting actions based on the feedback. I would recommend everybody to watch machine learning series as well as deep learning series, which will really help you answer artificial intelligence unit questions. The series is done in Tamil, but the complete content visible in the screen is in English. So it will be easy for you to follow even though you don't understand Tamil. In reinforcement learning, whenever you take some action, you receive something called a feedback. If the feedback is positive and asking you to move forward, you can go in the same way. If the feedback is negative, stating you are coming in the wrong route, then you have to take the alternate path. So based on the feedback only, the actions have to be taken. In that case, we can say these are adjusting actions based on continuous feedback. Okay, what will happen at the end of all these actions? You will go for a reward. So the more number of paths you have, the more number of traps can also be present inside the path. If you take a maze game, so you have to start from here and come out from here. You will have something like this and you will have some blocks in between and only one path will be taking you outside. Whenever you go and hit the obstacle, it is a feedback telling you not to take this path. Whenever you go to a path which has some way, it is a feedback telling yes, you are on the right path. So what is the maximum reward here? Getting out of the way. You can take rat and cheese game. So rat will be present here and the cheese will be present here. So the rat has to go to the cheese using a maze. So if the rat approaches a trap, there it will receive negative feedback. When it is approaching the cheese, it will go for a positive feedback. What is the reward that the rat is going to get? It is the cheese ultimately. Here there is dynamic learning. Based on the feedback, the actions are getting changed. Now think which is complex. Deep learning, which is going to learn from a training data and it is going to apply that knowledge to a new data. Is this complex? Or based on continuous feedbacks, you have to keep changing the actions here and there, and that too it has to happen dynamically. In this case, we can say deep learning is less complex compared to reinforcement learning. We can take it as this is less than option D, which means reinforcement learning is taking the highest complexity. This comparison is made using rule-based system, shallow neural networks, convolutional neural networks, and reinforcement learning. Now let's go for the comparison of the examples given. Spam email detection. What you are going to do? You are going to classify the email as either a normal mail or a spam. It's just a classification work that it is going to do. So it is the simplest task comparatively. Next is handwritten digit recognition. You know the digits between 0 to 9. Whenever a handwritten digit is going to be fed as an input, they are going to recognize which pattern it is going to stick on to. Compared to spam email detection, handwritten digit seems to be little complex. So this is digit recognition and this is classification. In digit recognition, you have a set of numbers from 0 to 9 and you have to just recognize which number it is. But in image classification, you have to classify. These are tables, these are chairs, these are human beings. This is sky, this is wall, this is painting, this is cat, this is dog. You have to classify everything. Compared to digit recognition, classification of images will be complex. Autonomous driving. Think there is no driver in your car and the car has to travel. So like robotic driving. We can easily say D will be the most complex one. Whether you are going with the order of the applications provided here or the algorithms provided here, the order is A, B, C, D, where A is the least complex and D is the most complex of these four examples. Since they are asking increasing complexity, we are starting from the smallest one and ending with the largest one. Option number 1, A, B, C, D will be the right answer. Next time, applications can be a separate question or the algorithms may turn out to be a separate question. You have to know the answer based on both the sides. That's why I am giving you the answer based on application as well as based on the algorithm used. Next question. Which of the following structures of knowledge representation are the most purely syntactic? It means which structure is going to follow some syntax they are asking. So knowledge representation is a topic in artificial intelligence unit where we have certain representation. So we will get an idea about all these four options. The first option, conceptual dependency is not concerned with syntactic considerations because it is going to focus on representing the meaning of the natural language expression. So whether it belongs to some grammar or some language, it doesn't care. Overall, the semantics of the particular sentence or semantics of the particular natural language expression is going to be focused here. So this focuses on the meaning, the semantics, and not on the syntax. This is what these 2 points say. Since they are asking which are the most purely syntactic, option A is going to be ruled out. So this one will not be in the right answer list. Next, we will see about predicate logic. Based on the knowledge we have from discrete structures and optimization unit, we can say it is about quantification. You would have seen the symbols like for, all, there is, all these are quantifiers. So predicate logic extends propositional logic by introducing predicates, variables and quantifiers. What is propositional logic made of? It is made up of conjunction, and operator, disjunction, or operator, then negation, the not operator. So it is extending by the use of quantifiers. It has a syntactic structure that determines the scope of quantifiers and binding of variables. So there is a rule to frame predicate logic. It is both syntactic and semantic. So whenever you express something, for all x square is less than or equal to x cube. Here this is a mathematical expression, but this states that it's applicable for all x. It is syntactically telling for all values of x, as well as the meaning we can get is it applies to each and every value of x. In that case, it is applicable for both syntax as well as for semantics. So this is just a mathematical expression I am telling you. Maybe for predicate I can say something as square of a number is less than cube of a number. If I write this in a statement like from, which is called as predicate, I can just apply it to predicate logic. So next time when there is a question, which representation is semantic, you can mark conceptual dependency and predicate logic as the answer. Next one, In knowledge representation, a slot and filler structure is used to organize information. Slot represents an attribute or property. Say for example, who is the author of the book? This will be the slot. The filler is the value associated with the slot. Author's name is XXX. So this will be the filler value and this will be the slot. The attribute name is the slot and the value associated with the slot will be called as filler. It is in the form of key value pair. So it's a pair, one is identifying the attribute and the other is identifying the value of the attribute. It is a syntactic structure. So predicate logic is syntactic and slot and filler is syntactic. Since there are only two options available in the choose the correct answer, we can go with option number 2, B and C only as the right answer. What about non-monotonic systems? So let's see about that. Monotonic means it is not going to change. Non-monotonic means it keeps on changing according to the situation. Non-monotonic systems are based on assumptions that results in tentative conclusions. It means whenever they make some statement, it is just purely based on assumption. It is not based on fact. If assumptions change, the conclusion might also change. It might change in the future. Non-monotonic is it keeps changing. What is the use of syntax? Syntax is a static structure. It will give you some kind of format. Format in the sense it will have a formal structure. Say if you take slot and filler, slot will be representing the attribute. So it will have a form like slot colon filler. This will stay always true. In predicate logic, to represent all the values of x, you have to use this symbol, means you have to use this. If they say there is a possibility of single value of x, you have to use this symbol, means you have to use it. So it is imposing some strict structure there. Non-monotonic systems don't have that strict structure because they tend to change according to the situation or condition. So we are not going to have non-monotonic systems also as syntactic structure. So we can rule out even D. Next question. For the fuzzy sets, they are given two sets here. They are asking for A intersection B. In the classic sets, A union B will be joining the sets A and B. A intersection B will be whatever is common in between A and B, those elements will be intersecting elements. Regarding fuzzy sets, the concept is different. For union, you have to choose the maximum of the elements, and for intersection, you have to choose the minimum of the elements. What is the maximum and minimum part? If both the sets have x1 element, whichever is maximum becomes the union choice. Whichever is minimum becomes the intersection choice. Let's see it as statement. The intersection of fuzzy sets A intersection B is equal to minimum of the value which is in set A and set B. So let's see the calculation now. Let's take the A set and let's take the B set. Now we will find the minimum of 0.3 and 0.5. Similarly 0.7 and 0.2, 0.4 and 0.5. This is with respect to x3, this is with respect to x2 and this is with respect to x1. Now what is the minimum value? For x1 it is 0.3, for x2 it is 0.2, for x3 it is 0.4. This will be the answer set. Where it is matching? It is matching in option number 4. Option number 4 will be the right answer. You should pick the same element from both the sets and then compare the value. Out of the values, whichever is smaller will be chosen for intersection. Next question. For the fuzzy set, the same A set is repeated here. The complement of A would be represented as, in classical sets, if A is going to have some element like 1, 2 and 3, A's complement will be not 1, 2 and 3. Except 1, 2 and 3, everything will be covered. In fuzzy set, complement will be 1 minus the value of the element. It means if I have 0.3 here, you have to take 1 minus 0.3 as the complement of x1 element. So we will see the calculation. A is equal to x1 has 0.3, x2 has 0.7, x3 has 0.4. The complement will be taken as 1 minus 0.3 in case of x1, 1 minus 0.7 in case of x2 and 1 minus 0.4 in case of x3. Now the answer will be x1 is 0.7, x2 is 0.3, x3 is 0.6. This is actually matching in option number 3. Option number 3 will be the right answer. What is the 0.37 or 4? What are they? They are actually called the membership values. In sets you have two possibilities. The element is either there or the element is not there. It is just like 0 and 1. 0 means it is not there, 1 means it is there. But in fuzzy sets you have membership values that lies between 0 to 1. The value will say how much membership it has. That is called as the degree of membership. So in this case x1 has 0.3 degree, x2 has 0.7 degree and x3 has 0.4 degree. So since it is with respect to the range 0 to 1, for calculating complement we subtract it from 1. Next question. The cardinality of a fuzzy set is. Actually this question is still in research. If you ask me, I will even mark option 4 not known as the answer. But let's interpret the option. When you say about a set, the set can be empty also. So there is a possibility of having 0. But can you tell all sets are empty? No. In that way we can rule out 1. In classical sets we have finite sets and infinite sets. Finite sets are when the elements are countable. Infinite is when you cannot count all those elements. Say for example, when they say it's a set of integer, it means it has 0, it has positive numbers, it has negative numbers too. Apart from that, can you say this is the starting or this is the ending? In computer science, you have representation for integer in computers. I am not asking about the range of integers in programming aspect. In general, in mathematics, do you have something like that? No. This should be minus infinity and this should be plus infinity. Is infinity a value? No. It's an extreme bound which we cannot say. You cannot say all sets are finite because sets can be infinite too. This is purely with regards to classical sets I am talking. At least in classical set, the element is either belonging to a particular set or it is not belonging to a particular set. But in fuzzy set we have memberships. Every element is associated with a degree of membership as I explained earlier. We cannot be so sure that every set will be finite. So we can also remove finite here. So instead of cardinality, today they are calculating something called scalar cardinality. It is the sum of the membership values of all the elements in the fuzzy set. Previously we saw a set, namely x1 is having 0.7, x2 is having 0.3 and x3 is having 0.6. Adding all these values together will be giving the scalar cardinality. So there are other cardinalities like relative cardinality, fuzzy cardinality, but there is no definition to cardinality of a fuzzy set. There are kinds of cardinality that can be found from the fuzzy set. This question is not about scalar cardinality, so we cannot take this definition. The statement that I saw in one of the fuzzy logic book. Since the cardinality of fuzzy sets on any universe means whenever you talk about a set A in classical sets, you will be placing it under a universal set. So this is for any universe. Since the cardinality of fuzzy sets on any universe is infinity, so this is giving you the cardinality of fuzzy sets. The cardinality of a fuzzy relation between two or more universes is also infinity. So this is about fuzzy relation. They are declaring that cardinality of a fuzzy relation based on the cardinality of fuzzy sets. So based on this statement from the book, we are going with option number 3 as the right answer. I am even striking out option number 4. Next question. What is a perceptron in artificial neural network? Let me again remind you the deep learning series available in the channel. I would have talked about perceptrons, single layer perceptron and multi-layer perceptrons. Now let's start. A double layer auto-associative neural network, a neural network that contains feedback, and auto-associative neural network, a single layer feed-forward neural network with pre-processing. The perceptron is a single layered feed-forward neural network. What is actually the single layer? The single layer is nothing but a set of neurons. This is a single layer. Feed forward means you will be moving from the input layer to the output layer. So this is feed forward, moving forward with the data. The pre-processing stage is not made of neurons. That's why it is not considered as a layer. We are just pre-processing the inputs that is going to be supplied to the input layer. From this we can mark option number 4 to be the right answer. What about auto-associative, feedback network, double layer network? Let's see. An auto-associative network is equivalent to a neural network that contains feedback. The definition of option 3 is option number 2. The number of feedback paths called as loops does not have to be 1. Maybe when there are 2 feedback paths, we might tell it as a double layer auto-associative neural network. If they ask you what is auto-associative neural network, you should be able to find the answer as neural network that contains feedback, because they are just telling it is equivalent to. It means it is going to have a similar structure. Next question. Backpropagation is a learning technique that adjusts weight in the neural network by propagating weight changes. Propagating in the sense where it is sending, they are asking. So when it is backpropagation, there is no use of forward movement. So both the forward movements will be taken out. Let's take a diagram. This is going to be the input layer. This is the activation function part. And this is going to be the output layer. This can be the hidden layer also. This will be the source. And this will be the destination. Destination is also called as sink. When you are going to process data, this is feed forwarding of information. This is what we called as feed forward network. Backpropagation is about propagating the errors backward from the sink to the source. You have to propagate it back to the input layer or to the source of the neural network. Sink to source will be the answer. So option number 2 will be the right answer. Let's take this to be input layer, output layer. This is hidden layer 1 and this is hidden layer 2. Suppose if there is going to be any error here, the errors will be backpropagated to this layer. So there is a possibility of backward from sink to hidden nodes here. But why are we marking sink to source? Whenever we are backpropagating the error, this will ultimately go to the input layer step by step. If there are multiple hidden nodes in between, we may send it to the hidden layer, but ultimately it will be propagated to the input layer only. The source will be the ultimate receiver. So we are going with the option sink to source and we are not marking sink to hidden nodes. I won't say backward from sink to hidden nodes is wrong. When option number 2 is not present here, out of 1, 3 and 4, I may mark option 4. But when option 2 is present, we have to stress that source will be the destination of the errors. So it will be traveling from sink to the source. Next question. Which of the following genetic algorithm operation is computationally most expensive? So when they say it is computationally most expensive, we can say there involves lots of calculations which may increase the time, or they can say this will occupy more space, more usage of resources too. So which of the operation is going to be most expensive? Let's see the genetic algorithm operation in the form of a flow chart. So first we have to select an initial population. Using that population, I have to calculate the fitness value of the individuals. From there I will go for selection, then for crossover, then for mutation operation. After that, I will check if some termination criteria is there. If the criteria is there, I will end the process. Else I will be again calculating the fitness value. So this is the general process. Now this initial population creation is initial population stage. Selection of subpopulation for mating is this selection. Convergence testing is this termination criteria. Reproduction to produce next generation will be this part. We can just take them together. Now let's see every stage. Initial population is actually selected by random. Random choice is not going to be most expensive and all. Not more computations will be occurring there. So in that case, we can rule out initial population creation. Next, calculating the fitness value. There are lots of membership functions that we have seen. There are lots of complex functions that we have not seen that involves in fitness value calculation part. So this is actually the computationally expensive part. as per the genetic algorithm process. Coming to selection. This is selection of subpopulation for mating. So after selecting only you will be setting to crossover. How does this selection happen? We have seen in unit outline video about 3 selection. So one is the roulette wheel selection, then the tournament selection, then rank selection. So at least we know 3 methods. This selection is going to be on some method and this is going to take some time or space, I could say. But this is not going to be an expensive computation because you are just going to select it. Selection of subpopulation is also not the most expensive computation. Next, we will together place crossover and mutation as reproduction to produce next generation. This is computationally expensive because you are going to get new offspring from existing parents in terms of genetic algorithm, or you are going to get a new solution from existing details in terms of problems. Reproduction part or the crossover mutation part will be computationally expensive. Next, what is termination criteria? It is just a condition. What kind of condition it can be? You can check whether an optimal value has been reached, or you can check whether the reproduction has crossed certain number of generation. When it touches maximum number of generation, you have to ultimately end the algorithm. So when it reaches an optimal value, you have to ultimately end the algorithm. Evaluation of condition will give rise to either yes or no. You need a if and else structure to explain this. All the calculations will be over in the previous stage. For example, let's check for optimal value. You are going to check if it is greater than something, stop. If it is not, iterate again. This is not going to be computationally expensive. We can also remove convergence testing. Convergence testing means you are just narrowing down it to some kind of test. Converge, narrow it down, we will say. So these are all big processes, we can say. You are just converging it to some kind of criteria. That is convergence testing. Option number 4. Reproduction to produce next generation will be the computationally most expensive operation. Next question. The parameter actual count is used in genetic algorithm for. There are 2 stages in this question. You are calculating the value of actual count in one operation. Calculation is done in one operation and the value that is calculated is used for another operation. They are not asking about where it is getting calculated. They are asking where do you use the calculated value. The previous problem, where is the optimum value is used? It is used in the termination condition to check whether we have to go for iteration or just end the algorithm. So the question is asking, you have already calculated actual count. Where are you going to use it? What is actual count? It refers to how many times a particular individual or a particular solution is going to appear in the population after these operations. So how many times an individual or a solution is going to appear is what actual count means. So we know there are 3 operations after fitness calculation. Selection, then crossover, then mutation. We are in selecting population now. Compute the probability of selection. How do you compute it? Say for example, if there are 3 individuals, namely I1, I2 and I3. You will have fitness value for them as F1, F2 and F3. Now the probability of selection of F1 will be F1 divided by F1 plus F2 plus F3. For F2 it will be F2 divided by F1 plus F2 plus F3. Similarly F3 it will have F3 divided by F1 plus F2 plus F3. So the summation will be F1 plus F2 plus F3 and the fitness value will be either F1 for the first one, F2 for the second one, F3 for the third one. F1 divided by the summation, F2 divided by the summation, F3 divided by the summation. This will give you the probability of selection. Now we have to compute the expected count for the entire population. You have to find the average of fitness value. Here you have found the summation of fitness value. How do you calculate average? Average is equal to sum divided by the number of people involved here. Here we are involving only 3 people, so this is sum by 3. So we have got average of fitness values. The expected count gives an idea of which population can be selected for further processing in the mating pool. What is expected count? the fitness value of the individual divided by the average of fitness values of all individuals. So from where do you get all those values? Only from the fitness part you are getting into selection. Now there comes the term actual count. Actual count is to be obtained to select the individuals which would participate in the crossover cycle using roulette wheel selection. This actually gives you the answer. The actual count is obtained in selection stage to select individuals to participate in which cycle? In crossover cycle. So the actual count is actually calculated in the selection operation and it is going to be used in the crossover operation. In case the question is where is the parameter calculated, you can say it is selecting population. When they have asked you where it is used, it is actually used in crossover. So now we can mark option 1 to be the right answer. Now let's see about the actual count. So this time the selection process is using roulette wheel selection. What is roulette wheel actually? They will just roll the wheel. There will be a pointer like this. So wherever the pointer is going to stand, that person will be selected. This is roulette wheel selection. So they have given some possibility. It's like a game only. The example was done with a string for some other problem. Imagine you are rolling it for 4 times. The first person is selected only once. So they are taking the actual count of string 1 is 1. It means this will occur once in the mating pool. Now they are rolling it again and again. Out of the 4, string 2 is occurring 2 times. This is for string 1. This is for string 2. Say for example, they are rolling it once, 1 is getting selected. They are rolling it for the second time, 2 is getting selected. When they are rolling it for the third time, again 2 is going to be selected. There are 2 selections of the same string. So we can say if the value of actual count is 2, it means that particular individual will occur twice in the mating pool. I said they will roll it 4 times. In that 3 count is finished. The 4th count goes to the 4th individual. That's why the 4th individual is given 1 here. It means that individual will occur once in the mating pool. Which individual did not have any chance in this wheel selection? Individual 3 did not have any chance. Whenever they rolled the wheel, string 1 occurred, string 2 occurred and string 4 occurred, but string 3 never occurred. It means the value is 0. What does 0 means? It does not occur in the mating pool. Now, based on the actual count number only, they are deciding how many times it will occur in the mating pool. This is what they are given. How many times a particular individual or a solution appears in the population is called actual count. These operation in the sense after the selection operation. Now let's see the diagram here. The first individual is having actual count of 1. So it is occurring only 1 time. The 4th individual is going to occur only 1 time. So the 4th number is mentioned only once. What about the actual count of individual 2? It is 2. So it is occurring 2 times here. Count 2. Count 1, count 1. How many times it is going to occur is actual count. This is actually the crossover operation that is performed to produce new offspring, in the sense new children. Where the actual count is calculated, it is calculated in selection operation used for crossover operation. So we are calculating it in one operation and using it in another operation. Next question. In genetic algorithms, crossover operation mask is used in. Let's understand what is crossover operation. This is used to create new solutions from the existing solutions. That is producing children from the parents. So they are already existing, from them we are going to create new solution. For the crossover operation, we will need at least 2 parents. So 2 parent crossover is crossover operation with 2 parents. What about 3 parent crossover? 3 parent crossover is where we will have 3 parents. Genetic algorithm is not only for reproduction in terms of biology. It is also a category of evolutionary algorithms, means whichever problems are considered more complex that cannot be solved by normal programming constructs can adopt this strategy to solve it. One good example I can say is timetable. Usually timetable generation softwares either run for a long time or they take up all the memory space and somehow hang the system. So timetable generation using genetic algorithm is a very popular topic when genetic algorithm was introduced in the field. When you want to feed the logic to the machine, you have to take care of the classes, you have to take care of the students, you have to take care of the teachers, you have to give them a balance so that one teacher doesn't work all the 8 hours. At the same time, the students have to be shuffled with certain subjects. Can you feed all these logics in if-else statement? It is quite not possible, right? In that case, we are going with genetic algorithm kind of thing. So when I say it is parent chromosome, it doesn't mean you have to think human beings as parents. It can be a solution to any problem, not only reproduction. So in this case, we'll go with 3-parent crossover. 3 parents are involved. So imagine one parent is black, one parent is grey and one parent is white here. The child will be a mixture of all the 3 parents. Generally for crossover, you will at least need 2 parent, parent 1 and parent 2. From them only they can go for a child. 2 parent is involving 2 parents. 3 parent is involving 3 parents. What is endpoint crossover? If you take a parent, the parent is split into 3. By how many points? This is point 1, this is point 2. I can say this is 2-point crossover because this parent is divided by 2 points, this parent is divided by 2 points, and even this would have been divided by 2 points. We cannot see this in black color. Since there are 2 points in the parent part, 1 point of the parent will stay as it is. The first point is staying as it is. We have black, grey, white. It is black, grey and white. Here it is grey, white and black. Similarly, the next shuffling will be white, black and grey. Since there are 2 points, we can say this is 2-point crossover. If there are n number of points, there are n-point crossover. While explaining all these things, did I use the term mask? No. What should the answer be now? It should be uniform crossover. We'll just see how it is. Each bit is selected randomly from one of the corresponding genes of the parent chromosomes. Let's see an example here. Let's take the binary encoding of the parent. This is parent 1 and this is parent 2. When they say 1-point crossover, only one part of the parent will be shuffled to produce children. Here we saw 2-point crossover, so 2 parts are exchanged. This part is exchanged and this part is exchanged. So instead of grey we had white here, instead of grey we had black here. Similarly, these 2 are changed, these 2 are changed. How many parts of the parent are going to be changed is what the 2-point or 3-point or n-point crossover is going to tell you. Here they are saying which part of the particular value is going to change. When the mask is 1, these 2 values will be swapped. We have 0 and 1 here. When the second position is 1, we are swapping it again. So this is 0 and 1 here. Let's take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now let's take the 5th position. We have 0 here. Parent 1 is 1, parent 2 is 0. Just check it is the same. But just consider the previous position 4. You should have a swap here. It is swapped. So whenever the mask has 1 bit, the positions of the gene will be swapped. Whenever it has 0, it will stay the same. So where mask is used, it is used in uniform crossover. There are also other examples. You will have 4, 5, 6. You will have 7, 8, 9. Then you will have mask as 1, 0, 1. The offspring will be 7, 5, 9. Here it will be 4, 8, 6. So we are swapping only the ones places between parent 1 and parent 2. It is not only with respect to 0, 1. It could be even in real encoding, integer encoding, binary encoding or permutation encoding. The strategy is not a problem here, but the use of mask is what you have to understand. Option number 3, uniform crossover will be the right answer. In uniform crossover operation, we are using mask. Next question. For the following parents in figure 1 and figure 2. Now they have given the parents in the form of zeros and ones. And they have marked the crossover point. Wherever the parent 1 is marked, the same place parent 2 is also marked. So they have mentioned this to be the crossover point. Similarly, this to be the crossover point. What they are asking is whether this is 2-point crossover, 1-point crossover, n-point crossover or uniform crossover. In uniform crossover, you need something called a mask. Just now we saw. So this is out of the race. How many divisions are present here? Only one division is present here. So there cannot be n-point. We will rule out even 3. What is 1-point crossover? Only one crossover point is present. All data beyond that point is swapped between the 2 chromosomes. Let's take 2 chromosomes, namely chromosome 1 and chromosome 2. They are in different colors for better clarity. Here we are placing the point in the same position. Now chromosome 1 will have this value as it is, and this value will be taken from chromosome 2. Similarly, this part of chromosome 2 is staying as it is. This part has been taken from chromosome 1. All data beyond that point, after this point, is swapped between the 2 chromosomes. It is swapped. Do you get the meaning now? So, what is 1-point crossover? Only one point is present. Only one division is present. Take these two together, these two together. It is having only one division. This is also having only one division. It means figure 2 is 1-point crossover of figure 1. Option number 2 will be the right answer. Now let's see about 2-point crossover. 2 random points are chosen. Here it is 1, here it is 1. So 2 points are there. A specific case of n-point crossover technique. Since n is equal to 1, it becomes 1-point crossover, and when n is equal to 2, it becomes 2-point crossover. They have kept this part as it is and this part as it is. They are just the same. These two parts are swapped. 110, 100 is here. 011, 001. This part is actually here. Now let me take this to be x, this to be y, this to be z. This is going to be A, this is going to be B, and this is going to be C. Now let's take X, Y, Z, A, B, C. This is 2-point. What kind of offsprings they have given? They have given X, B, Z, A, Y, C. They have interchanged only these two. There are also other possibility. I can keep Y, Z as it is, B, C as it is, and I can exchange A and X. This is one possibility. Similarly, XY I can keep as it is, AB I can keep as it is, I can exchange C and Z also. There are also other possibilities where I can keep only X and A as it is. Here B, C can accompany, and here Y, Z can accompany. There are lots of possibilities that can be taken from 2-point crossover. For example, they have given only one way, which is XBZ and AYC, and another way also you can do. You can just have ZC static here and then move AB up and XY here. Here we have only one division, and here we have only one division. This is also 1 point. This is also 1 point. You are swapping only 010 to this position and 111 to this position. 1 point will be fixed and another will be swapped. 2 point means one will be fixed and 2 will be swapped. In this case, we can even rule out option number 1. This is actually a 1-point crossover because there is only one crossover point that is present in figure 1 as well as in figure 2. With this, we are completing Unit 10 solutions.